Hello, this is the recording session of the class. This is more or less a little bit review of last week's session, but I'll go over with this early vision and especially with convolution. This coverage is especially very closely related to the lab session you will do after this lecture session. So I'm recording this lecture about an hour or hour and a half. After that, there will be the lab session. That handout is already given to you. So with that, I'm sure that you can understand it better. So again, that what we are doing is early vision, more of chapter 3 of the Zelsky's book. And here we said that algorithmic step of computer vision is that first step is image capture. So that's why we talked about human vision and machine vision or camera, the concepts. So every image we are processing somehow captured from nature or from reality using one type or other of the camera. There are a lot of good technology made for the better quality camera so that it can cover a longer range and in the different the lighting condition, whether it is very dark or light it can handle, or it can handle the very speedy or the quick movement, so it can capture the big video. So anyway, this computer vision class is a way of capture the image to be converted such a way we understand what the we actually means machine. So machine with the algorithm will understand what's in there. So substituting human activities of seeing and recognizing. Anyway, so image capture and then early vision that we're talking about, we got to prepare. So when you are doing surgery or some kind of building a house or doing some party, you need the preparation. So in a way, lower level vision is more like the preparing for the event. So we have an image captured from the camera. Then maybe we need a lot of things to do for preparation, like oh, it is too dirty, too dark. We make it somehow massage. There are too many dots and unnecessary noisy part or the kind of a dirty part of the image. We would like to remove them so that our processing can be easier and more accurate. So that process includes a lot of conversion of the pixel value, and very important is a noise reduction, reduce the noise. The noise here means that it's not a part of a meaningful image. It's like a background with some kind of a fluctuation or some mistake or some problem with the lens, that kind of thing. So we want to remove it. Then simplifying the picture, if it's too thick, well, first of all, that we got to make a separation between background and a certain object. So we want to recognize face, for example. That first thing to do is that getting those outline. So out of those picture, like my picture here, we got to have those the outline of a face being detected or isolated. That is done by so-called edge detection. This is very well researched and a lot of very smart algorithms that will cover that maybe next time. But today they will go with cleaning and thinning. Sometimes there are too much thickness on the line or certain objects, and we want to simplify that into as thin as possible. After that is done, then middle level goes that we want to know that what object or not object and calculate its geometry, what is up, what is down, what is the left, and what is behind, what is the front. Are they in distance or in the close location, that kind of thing. And of course, the final thing is that the recognizing the objects. So we want to make a conclusion, say, aha, this is the picture where they like a face of the somebody, and that somebody happens to be my friend, or it is somebody that I don't like, or somebody I like, whatever like that. We want to make the understanding done, or the decision done more accurately. So after all, I said many times that computer vision is the process of understanding the picture from the captured image. Okay, so we said things like this is the actual picture, then by thinning, this is edge detection. Actually, the edge detection is the very simple way being done, and a few of those the examples that we are pulling up. The canny edge detection is the one that you may use in the case of the the lab session. Then eventually you put that into some kind of model of objects. So as much as you can give some kind of objects identified and its relative position or geometry, figured it out, and that's the process of that's the second step of middle vision. So first vision is just making it clean up our images. And so after that, geometry being understood, and finally the object is understood. That's something that we talked about last time. So what we are doing, chapter 3 is that we want to do some kind of a cleaning up or preparation of the image before we go with the decision making. Is that first of all that we can operate on pixel value. So we increase, decrease, or divide, or add some value, that kind of intensity value, or color value. It is too reddish, then let's make it reduce to the redness, or it is too yellowish, then usually yellow is the color that doesn't have the blue. Red and green makes it the yellow. So we add some more blue that can reduce some kind of yellowish tint. Reduced, that kind of adjusting. That is what we are doing by changing the value of a pixel. Then the linear filtering, this is the most important one. So linear filtering wise, that we can have each case that certain value, if it's greater than a certain value, then knock it up, or they remove it, and it is in the middle value, then take it, then maybe the case. So that's the linear filtering. But more important, or more frequently done, is a neighborhood operation. In other words, that we have a pixel value, so but pixel doesn't exist by itself. It exists with the neighbors. So suppose I want to recalculate the value of this pixel value, then the one method that we've done by first two is that just with some equation or some changes, some transformation that change this value itself without thinking others, and go to this one and they apply same formula for changing the value. But more likely, this part of the images keep changing. Like in this image, this part is some line, this is the dark part, and the place here is the background that's white, and the wall slightly different color. All those things are happening. So in a way, the pixel value, to make it cleaned up and more easier for decision making, better be done in respect to neighboring pixel value. So that is called the neighborhood operation. Then there was this thing called the filter. So filter is more like a grid, and that has certain values. So you use those grid superimposed over the actual the image, and according to this filter characteristics, you change the value. That's the idea. So that is actually convolution. So we're going to talk about this one a lot. Another very important one, this is covered in later part of this session, is a Fourier transformation. This is used extensively for many other applications, but in computer vision, Fourier transformation is also used. The mathematics is a little complex, but the core concept is something we can understand. So that's the part I will explain. And then I don't know why I put that median filter separated out. That's part of those the filtering, but it's more like a linear filtering, neighborhood operation. So you take a pixel value of neighbor and get the median value, but that works really remarkably, surprisingly well. So it's not bad. Then Gaussian and Laplacian, the pyramids. So this one, when you look at the Google map or Google Earth, then you see the big picture. There's the whole Earth is in one screen, and then you start zooming in. Then you get the more detail of some Asian continent, and go further. Then you can go to the Mongolia as one whole chunk. Go even further and go to Ulaanbaatar, even more than a specific location of Freie University, even more than maybe backyard or the main campus of the university. So it goes all the way close up, more zoom out. You look from the sky, it's more like airplane, goes closer or go out. Maybe a helicopter is a better word than airplane, but anyway, that's the kind of logic is Gaussian and the Laplacian, the pyramid, and then sharpening the image by global optimization. So there are so many techniques being used in early stage. So yeah, I will cover as many the techniques as possible. Then there's a motivation was noise reduction is very important. So noise is the, as I said, undesirable elements in the picture. So here there's a lady with a hat, and then we want to recognize her in a sense. Then those eye part, nose part, mouth part, all important. But in the face part, there's speckles. There's some kind of dots. That doesn't help. Well, in general, with this one alone, our human eyes can still recognize her pretty well, and the neck here and the body here, maybe not that difficult. But if we want to have a little more detail and more of a, say, for example, what is in her hat, the decoration, then we may want to make sure that this one doesn't have any unnecessary or the part of the picture that doesn't belong to real picture. That is a noise. Noise is some sound you don't care, doesn't belong to whatever the situation, or actually that makes you confused. So same thing, that there's a noise in the image means that the part of display that we want to remove so that we make it cleaner. So this one has a little more clear than the other one. It's not perfect, but there's some changes. So somehow that we can reduce the noise. So there's many filters, and median filter again is a good one, and the Gaussian or the Gaussian filter, bilateral filter, that will work pretty well. So the last one is much clearer, and the whole picture is very fresh, in a way, crisp, what they call crisp means sharp. So that kind of the improvement we can expect. So what we do, then I told you this one was that there's a given original picture here, then we can change the color bit or a little sharpen more, blur it more. Sometimes you want to make it blurry. For example, in like a Zoom session or WebEx session. There's a lot of background. You see that my background there is the one small bookcase and little door. But I don't want my background to be displayed. Then we want to make our background being blurred out. So the detail is hidden, so to speak. This one is a little more sharpened, and this one is the rotated or changed, geometrically changed. So there are so many different things you can do for the given image that you have captured. Okay, so the first one, actually the chapter 3, section 1 talks about pixel or point data operation. So G is the function, X is the pixel value. So G of ij, this is a location. Of course, that our picture invariably is two-dimensional and have rows and the columns. This one is a row and the column. So you have ith row, just column thing. Then that value will change based on certain functions. So the grid G, so G whole thing we call G as the grid, as a matrix. Then we change into the H matrix, and in doing so, we need a function f. So that function can be very simple function, like very often the affine form is that you have a multiplier and some kind of adder, or the additive components. Or you can have the additive component also be function of it's a variable. So you can make this the more sophisticated the operation on pixel value. Well, all in all, the histogram equalization that I'm gonna tell you and demonstrate is actually a good example of this pixel or point data operation. Then so in doing the pointer adjustment, the value will be changing and uniform increasing, decreasing of the values, or sometimes it can be the function of the location, but in general that this is uniform. So after collecting overall the information, so like a histogram, in the lab then you will see how to work with the histogram, how to create one and use the histogram, and then using histogram that you can equalize or spreading it out. Then of course there are many colors, you know, is a red, green, and blue as 3 primary color components, and with those the component worked separately or applied separately. Maybe I told you before, but red and green has pretty high energy level, but blue has very low energy level. So sometimes the blue gives more of a, so to speak, noise or blur. So some sunglasses, when you the sunglasses are automatically filters all the blue part, so the things look sharper, clearer. Of course, the bad thing about it is that any blue colored object will look black, so that's no good. But anyway, that's the idea, that energy level is different. Then also that this is the color correction is sometimes needed as it goes toward the corner or in a high intensity of the color value, then that the human eye cannot respond well, so need some kind of a color corrections. So this one is done in computer graphics, but we are not covering here. Then composing and the matting. Matting means that many scene or many of the pictures all combined together, like an album or panoramic view. So you can have multiple images composed together, especially for the video. This is very essential to detect any kind of a motion or some kind of a changes from time to time. So this good thing about is that time changes and the scene will change, and the whatever part that's changed is something moving or something dynamic. So that kind of a pointer adjustment is needed for the earlier stage of the image processing here. And then, so composing and the matting is that combine different images into one, especially the background part together on the new faces or new objects. And then very important frequently that is that the transparency, level of transparency, so how transparent they are. So is whatever on the back be shown up or not. So some picture is very transparent, some of them is blocked like that one. So you can change that by changing the pixel values. And of course that by making the background not transparent, then you can make your the object look much clearer. But at the same time, the background removal gets harder. So you got to know where to find the best value of background transparencies like that. Then here goes the histogram equalization. Again, that the lab session will talk about histogram equalization. Histogram, by definition, is that those bar graph of frequencies. So here, x-axis is the value. So what would be value? Of course, it's a pixel value. So it depends on the pixel value, pixel value, but beginning with 0, that's complete darkness, to highest can be depending on how many bits per pixel. That typically 8-bit, that's 1 byte per pixel. So 250, not 6, but 5, because 255 is 1111111 about 8 bits. So this one, of course, is 0000000. So usually we go by the hexadecimal of 00. This one is F like that, right? This one, the 1111 is F. So in hexadecimal. So anyway, the value is here, here. So maximum value is 255, say. Then this is the frequency. So how many pixels there are, that depends. So suppose that you got a picture typically 1024 and then about the 840, something like that. Then this is close to the 1 million pixel or 1 megapixel. So total number of pixels will be 1 million. Then the depending on the values here, some here you don't have much of the light, the dark one. The smaller is the dark. Then this part, then there are the lighter one, and there are certain locations are peaked. The histogram equalization means that we have a certain range of color that can express, but it's just concentrated in one area. Then we want to spread it out. That's equalization. So here is an example that this kind of a picture, when we look at it, there are mostly some dark part that is hitting in here, and the white part goes little dark, the gray part actually, little brighter part goes on here. It's a reverse of that one. So if you change this one into binary, either 0 or 1, then this one will definitely become the dark, and this one will be all light white. But when you reverse it, then this 0 become 1, 1 becomes 0. Then this dark part become 1, the bright one, and then all the little brighter one will be black or dark. Here's the dark part, that is light here. So there's a thing called the threshold. So, given this is a frequency, and here's a pixel value, and then we see one big peak and another big peak, then whenever we got two peak, then we find the middle ground and cut it. So any value below this one, like here 100, will be taken a value of 0, and anything above 100 in this case, or actually it looks more like a 90 something, then it'll take a value of 1. That way we can make a black and white with a binary value. But in general, we don't want that binary 0-1 picture, but rather grayscale or colors. So here's the different expressions with the color and the backgrounds, and by histogram equalization, here we see a little better spread of those color operations. But even better here is that there's a lady, in general, this one is pretty dark. It's most dark, and the part of her face is pretty dark. So there are a lot of dark. And then not much of a brighter part. This part is all empty. So what do? We are increasing value. So multiply with a certain constant, like three times or twice of that one. And then each one will be adding up or pushing up. And the interval will increase in here. So the result of that is this, much brighter, much better, isn't it? So here, the whole face has become much lighter. So this is a good thing about so-called histogram equalization. So you take a picture and analyze within that by pixel value count, not you, but the machine will count, but the pixel intensity, and make this those frequency, value histograms and histogram. Then it come when we got everything combined together with so many different level and the many pixel value here, then we got a pretty smooth curve. In the lab, you will do the exercise of actually creating a histogram by hand calculating. So of course that our grid is just a small 10 by 10, but still it can be done. Even more spectacular is that this is something you will run using the OpenCV with the Python. So this is the original picture. I showed this picture before. So this one is it's 0-1 or something like that. I think 101, something like that. Anyway, so this picture, when we look at it, we don't see much, isn't it true? But there's looks like some picture, but it isn't much. But it's a very dark picture. Maybe you may have thrown away if this is the kind of picture. But if we have no other choice, then when we put the histogram, actually I was using the previous one. It is mostly dark, and the lighter part is all empty. So okay, let's squeeze it out. So histogram is spreading it out. Again, this is not coming directly from this picture. Actually, I should have done with the picture. I have a software that I can generate the histogram, but just to show the illustration. So anyway, by spreading this one out, then this is what it looked like. So see what happens. That from the dark part of this picture, that this one shows much more, surprisingly a lot of detail. So here you see something, a little blob in here and a little bit blob in here. What are they? What turned out to be is somebody's head. And this blob happens to be a kind of a empty space, and this in general, this one is a sky, and this part there's a little bit on here. That one is something, but there's a part of part of the animal, cow or those animal here, and also all those detail is not given in here. Pixel value wise, it is existing, but we couldn't recognize it because they are so close to each other. But now by spreading it out, we could make it much more clear. So that was the idea about the histogram equalization. You will run this program, and it's pretty easy if you use a CV. So the concept of making a histogram that's counting every pixel, make a range and count them, and then move it to the spreading out. That's a pretty much involved work, but nevertheless, once you do it, you will get pretty much good results. And definitely the machine vision can they give better results of identifying the objects in the picture. Okay, then convolution. The convolution, I did it last time, and hopefully you got it, but just in case you don't, or even if you got it, but still it's not a bad idea to review it. Convolution is this one is convolving, like that one. You convolve, go around, con together, and turn. Together we turn. Make sense? So con together. And the volve is a turn. So let's dance together. That may be the idea. So in that case, that what we have is an original picture here, source pixel it says, and then this is a convolution or template sometimes called. So this template, or sometimes called the matrix, or depending on the usage, we may call that a filter. So canny filter, or the cursor filter, things like that, the filter. But anyway, it is the formal name is convolution. So in a way that this small template and the main picture is dancing together, turning together. So turning together means this one multiplied by that, and then this one multiplies by that, like that. So for what? We are interested one in the middle. This given pixel is a one good value. So in that case, that if for whatever reason, this is our filter. Actually, this is for the edge detection part. So we have this is the filter of our convolution. Then we multiply this one by that. So it's just a superimpose it. And this guy with that, and this one with this. So this is a 3 by 3, 9 element portion of source pixels will be superimposed with this template, and each value will be multiplied, just like the 4 times 0, and 0 times 0, 0 times 0, 0 times 0, and 0 times 1. So what is given, first one is from the template, and the second one is in the source. So last number is 2, and then the last number in the source, the template, is -4. So you multiply like that one, then you got a 4 times 0 is 0, 0, 0, 0, and 0, 0. Well, there are so many zeros, there is much. Then the only valid one is the last one. This one is non-zero, and this is non-zero. So by multiplying and adding them all, you are adding 8 zeros, and the last one -8. So we change the pixel value. It was 1 now into 8. So isn't it terrible? It's a wrong number. Well, we are not necessarily filtering. This is a special kind of filter. So there is a reason. In other words, that this is not, one does not constitute any kind of a special unit, or actually means it is drastic changes. So anyway, each filter has a design based on certain logic. So we'll see that there are different varieties. But convolution is very important, and it is essential in many parts of this computer vision and image processing. That's why we are spending lab time and lecture time twice. So convolution is that the image be the kernel. Yeah, actually, sometimes those things are called kernel. Output of the f with g is denoted as f star g. Actually, this star g in the lab documentation, I used the star, but for whatever reason, that it is keep changing into this star, so I didn't change it. But anyway, it's supposed to be star for the symbol of convolution. Actually, this the reason why it's a star is multiplication. After all, we are multiplying. So in here, f and g. So one of them is the template or the kernel or this convolution, and the other one is the source image. So we have actually f is the source energy, the source pixel, and then G is the template or kernel. So we say so F is the image and G is the kernel. I already have that one. So here F, then there's a current M, location of M and N, and then the kernel has a K and L of left and right, left and right. So in a way, we got a loop of a 1, 0, -1. So here's say 3, 4, 5, the row, and 7, 8, 9. This is arbitrary number, please don't. So we are interested in the location 4 and 8. The value will be 4 minus 3, so it's a case of -1, and then -0 here, and then 5 plus 1. Here's the y is -1, and the m is -1, g is -1, n is -1, and then here. So here's one less, and one here. This location is from current location. This is in a way the center. Then one less, and then in terms of this direction or the row wise, it is one less, and then y wise it is one the less or the greater. Sometimes that in the processing, we in geometry we say this is a 0, 0, 1, 2, 3, 4. We may want to go that way, and the 1, 2, 3, 4. So this direction, everybody, though when you go to the right, this is 0, 1, 2, 3, 4. But this often there's the raster graphics, the typical computer graphics goes top to bottom the order. So this is 0, 1, 2, 3, 4. It can be like that. But logically or model-wise, we can make it. This is a plus, this is minus. We can do whatever. So this one, I just spend that time trying to explain the meaning of this symbol. So in a way, that the K, the summation, see here, there's a K. So K equals 0, 1, minus 1, 0, plus 1. Sorry about it. Let's do it again. Erase it. This one, K equals minus 1, 0, 1. L is minus 1, 0, 1, like that one. So go left to right, like that one. It can be -2, -1, 0, 1, 2. And then L is -2, -1, 0, 1, 2. That means our template or kernel or convolution can be 5 by 5. So it can be larger. Sometimes it can be 17 by 17. Usually odd numbers so that it is symmetric. So these are functions that you can sum it up to 2 different functions if necessary. So this one is for the pixel value changes, and then similar to what we see in the Fourier transformation part. So I'll skip this part. So in that case, moving average. Moving average means that replaces pixel with a weighted average of its neighbor. So this kind of thing is changing the center value as we go on. That is called the moving average. So this case is most common one is a box filter. So you are adding the value. So in other words, this is our source pixel. So to get the value of this one, what you do is that we are adding all 9, all the neighbors. Let me draw it again. Like that. So suppose that I want to get the value of this pixel, then we got a 3 by 3 grid. So add all those 9 components or 9 pixel value. Of course, then that will blow up whole pixel value by the 9 times. So we divide it by 9 to average out. So this is called the average filter, or sometimes called the box filter. So here's a pixels, and we have a 0, 0, 0, 0, 1, 0, 0, 0, 0, like that. Then definitely all the other neighbors doesn't get contribute excuse me, contribute anything. Only itself will be kind of replaced, or the valued exactly as original. So no changes. So this is no changes. This one is blown up to be the different scale. But anyway, so this kind of a thing is called the identity filter. So there's no reason why you apply identity filter, but sometimes there are cases as a part of a multiple operation, it can be used as one of the filters. Then if it is a 1 on the right hand side in the filter, what would happen? Well, understandably, that we have suppose that we have this 3 by 3, and I put this is the center value is what we had in mind, but because of a 1 in here, the result is that the value on the right will be moving. So in a way, it's shifting to your left just a bit. Think about it. So every pixel will be shifting by 1 unit. That is the idea. We don't see much differences, but it is shifting. Then if it's a 1, 1, 1, 1, that's average. What's the results of that? Usually, unless you do something special, then usually it's a blurring out. So a little bit of blurry, not as sharp, because it's all averaged out. So near 1 is all mixed up together. Then one very good thing, or the very frequently being done, is that focus on itself with twice of the value. Itself minus 1 over 9. What happens here? Then total of this one is 1, isn't it? I mean, this 1, 1, 1 plus 1, 1, 1, so there's 9. So this whole chunk is more like a 9. I mean, they're 9, and 1 over 9, so it's a 1. and then you are focusing on this one. This one is twice. So magnitude-wise, it is 2. In other words, that suppose the pixel value is something around 10, then this becomes 20. And this one is a 10, 10, 10, 10, 10 around that. Then it will be the 9 over 10, 90. So you divide by 9. So it is again 10-ish. So you subtract it, then it becomes 1. So it's become scale-wise is original. But anyway, what is good about it? You are focusing on the middle part, and the side one will be kind of removed, or it's a blurry factor will be the removed. So in a way that you got a little more, in a way, emphasized, and we see detail. Of course, we don't necessarily like this one better than this, but still we see much clearer, and a certain part got emphasized or exaggerated. So it is differences with the local averages. So current value and its area value subtracted. Sometimes that gives a much clearer pictures. And then sharpening can be done by having focus on main part, and then removing the surround as average, or by increasing itself by certain value, certain numbers. So there are some other sharpening filters. I'll explain that later. And the smoothing with the box filter. So this is the original picture like that one. Then we want to be smoothing or blurring, overall picture being somehow blurred out. It can be done by you just remove it yourself, and all the rest of them goes around it. So 1, 1, 1, 1, and just 0 in the center. Then you can give more of giving out the surrounding values. So it's become blobs. And then, so the smoothing with the box filter can be done by those blob part being more of the kind of emphasize on the center, and then less on the away from it. So this idea is pretty much like the Gaussian. Gaussian means it is normal distribution. So using that kind of filter, things get much more smoother. There's no sharp changes, because so it's a big chunk is moving around and making the covering big area and overlapping that big area makes a value similar there in the neighborhood. So there's no sharp changes. So that makes things look more smooth. Then I talked about the different type of the filters. There are so many different filters, but so one is a linear. You can go row by row by row instead of a grid. But this is also linear convolution. But more they are using this box filter. So 1 over k squared, that means that we have a k. So if k equals 5. K is 5, then this is going to be 25, 5 times 5, or it can be 7. That's 7 times 7 is 49 elements, things like that. So the bigger is the grid or box, then it will be more smooth in a way. Then this one is bilinear. So in that case, that you emphasize the middle part more than the farther away it goes, it is more blurred or less contributing. So that is the idea about this bilinear filter. So you will see. So it is more like it's a very small scale, but it's like that. But this one is a similar idea. So I told you. So 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. So middle part is higher, lower, and both are symmetric. So it's much like that. Then the middle part gets the larger values. So in a way, the previous value times 4, so to speak. Then the previous value times 6, the 4 times 6, 24, 6 times 6, 36, 4 times 6, 25, like that one. Again, this symmetric. So center value is the highest. So highest contribution, and the rest of them is less. But the farther away, it contributes less. So the total number, you add up 14641. Actually add that. That one is already the 16, and this is 16, and then this one will be 4 times of 16. That is the 56. Things like that. You add them all, that become total 256. Like that one. So you got to normalize it or back to the original scale. Then this one is edge detection. So Sobel, or actually Sobel is not used these days much, so it's a Kenny operator. That's what we're going to use for the lab session. So you make it the negative value, and then you just contribute nothing in the right hand side. So by doing this way, any kind of sharp change exists, if any. You keep going on and on and on, and checking previous one and the next one in the middle part, left side and right side is really different, then this value will be getting larger, isn't it? So by doing this way, that you can get the edge detected. So there are many researchers that looked for different type of equation or function to make it useful, and ended up just getting this. Then this one is more of a corner, so it is the 4 in the middle is the biggest one, and the negative one in the directed direction. This is -2, and then diagonal direction is a 1, like that one. That gives completely blurred out. So original picture here, and then that ended up just getting this much, like that. And the result of filtering wise, then there's another one. I don't know whether we, in the lab part that I talked about, there's dilation and where are you? The other one. It is a blurry, the effect of blurry and the sharpening. That's a C, and then T is a smoothing with the edge, the preserving filter. And the binary image, you make that on into the binary. That's more like that. That's F. Then this one, and the dilation and the erosion. There's no erosion in here. So actually, erosion and the dilation goes together. Dilation is make it blurred. It's much like your ink is got with the water. If you write something on the wet surface, then your ink get the spreading it out. That is actually dilation. When you have any reason to go to the eye doctors and they want to see inside your eyes, then your pupils usually is closed, harder to see. So they are giving you a drop that makes your pupil go widen. That's called the dilating, so blurring it out. Then the erosion is that you have some part, but it's washing it out and make it smaller, shorter. That is called erosion. So erosion and the dilation that works together. So there is a sample example. I think in OpenCV, the labeling or the name has been somehow switched, because I tried many examples, and then the result of dilation is more like a erosion, and the results of erosional function is more like a dilation. So I switched those names myself. But anyway, I hate to say that they were wrong, but looks like it doesn't look. Okay, then normal distribution of Gaussian can also making this normal distributed, so-called the blob, and make it smoothing it out. So in the statistics, I don't know whether you learned it or not, but the larger is this distribution or the standard deviation, it is spreading out more. So the bigger is the sigma, then you will expect a much more blob. Actually, there's a normal distribution and the Gaussian distribution is the same thing, so to speak. Gaussian is they are done by the Gauss, the German, the mathematician, and from there later they have most of the natural phenomenon comes when to follow that this kind of equation, 1 over square root of 2 pi sigma, and then exponentiation of minus then certain mean value and twice of the standard deviation, that kind of thing. So this one is the frequent, so it's given a name of normal distribution by the statistician. So in here again, the center part is pretty big compared to the others, and then the farther away from the center, the value gets smaller. If this is larger, then it'll spread out more, so it'll go further down to smaller value. So if this one is large, small, then this gets bigger, and the other one is this one center gets bigger, and the other one gets smaller. If it is big, then center gets small, and the other one gets big, like that one. So that kernel being used, so this one is a 5 by 5 kernel that can be used for the filtering, and the result of so-called cleaning is more like the blobbing it out. If there are so many complex objects, then you may want to try that the Gaussian the kernel. But the frequently used in there's a pepper. The bilateral is a similar effect that the pepper and the salt, a type of noise, can be removed. So what kind of a kernel to use? That is one of the big issues here. And so the bell-shaped curve, and then depending on the mean filtering or Gaussian filtering. So it's the average. This is original, and the averaging goes more like that. It's a little sharper, and then this one is cleaner, more like all the detailed the dirt or the noise is gone, but overall picture is a little blurry. So I don't think we need more on that. Then this is the example of calculating the convolution. So we are doing it in the lab part, and just after you doing it last week and this week, then you will be pretty much comfortable about this convolution part. Okay. And then again, the salt and the pepper noise can be removed by the Gaussian filter or bilateral. Bilateral is a similar kind of the Gaussian function. Then, so it's a Gaussian noise. What it is that the overall, suppose that we are going and then plotting the intensity. This is the intensity. So black is a dark low, and the little white thing, so it goes up. So up, and so in this line, this is a specific line. Each line, the intensity can be plotted. So here, there's a little white thing, so it is picked up, then dark for a while, and then this white, this pepper part is white. This one is here, then little dark here. That is this gap in between. And then this part is going up and down. There's a little, the complex textures goes up and down a bit. And then this dark part, yeah, this one just hits it, but somehow here's the dark part, and this white part and the dark part that goes in here. But if it is noisy, or that you made the Gaussian the noise added to, then it is, the curve is not that kind of a smooth, but there's a lot of up and downs because there's a flex. So it's not flat, uniform, the darkness, but there's a dark and white, dark white, dark white. So there's some vibration, and there's some vibration, sometimes pretty dark, and then sometimes very high, like that one. So when you look at the curve itself, then you see whether there's a noise or not. Actually, that's when Fourier transformation can remove this noise. So that's another technique be used. Anyway, so the Gaussian noise can be done by the different filter with the different sigma values. So if this one is a lowest sigma, that's a very high peak near the center, and this one this one is a sigma 0.22. So no smoothing, then this looks like that. But in here with a sigma of 1, then it gets a little smoother, and the color be distributed. And the 2, then is the things are spread a little bit better. So in a way that the large standard deviation makes it more blurry a little bit. The detail, the sharpness of those edge is gone. And the salt noise can be reduced by this the Gaussian filter. Then median filter. Median filter, again, you will do the exercise. Median is the value in the middle. So we got, this is the part of the main pixel, main original image pixel. So we got a 3 by 3 pixel image here. Then you arrange it in smallest to the largest. So here, smallest one is 10, next is a 15, and there's a 20, so too easy. Then 23 and the 27 and the 30, 31, 33, and the 90, the center one is highest one. So in a way, compared to the nearby pixels, the current value is pretty large. So you can do the averaging, but averaging doesn't do very sharp image. So rather, let's make it flatten. So 10, 15, 20, 30, 23, like that one. There are 9 values. So then 5th value is just in the middle. In the middle, that's a median, ranked in the middle. So if you change this one, 90 become 27. Then everything is 10, 15s, like that. Only the middle part was pretty high. So it's more like the white dot that pixel looks like, because compared to its background or surroundings, it got higher pixel values. So it looks like it is a small dot. So no good. So rather that you will do change that one into median. As I told you, that this is pretty simple operation, and it works pretty good. So that's is a linear filter? Is not necessarily. It is the grid or neighborhood filter. But anyway, advantage is that I did the last time this one too. One bad value or the outlier will move the average pushed up. In the median, then this one, then one is very much of an outlier, but it'll be just a flatten out. Then in here, this one will be the median in the middle. So it's a characteristic is all taken care of. But if it is a mean, then it will become smoothing it out. So contrast is lost. So sometimes it's not very good. So as I said, median filter works pretty good. And you can write a very simple program of calculating median. You do a little sorting and get the middle value. And then they replace the current pixel value with that median value. So median filter, if there's a lot of noise here, we see a lot of freckles. There's peppers have a lot of those noises. So they're actually more of a pepper noise, salt and pepper. There's a salt and there's pepper. So there's a lot of this dark one going down and up and down like that. If use the median filter, average may give this whole thing a little bit higher or lower. But if it is a median, then it goes pretty clear, and the trend is given pretty well. So much smoother, clean. So we wanted that our stage here is cleaning, reduce the noise. So here, making the differences between Gaussian and the median, and you can make a judgment, but median looks better, isn't it? And the calculation is even simpler. So that's a good advantage. And the median filter, that this is what the original looked like, a real bad case. And we could have done various techniques to make it better, but simple median filter gives this much. Then after this one, then we use some Gaussian filter to get rid of those some of those the salt, pepper, the noise. Then we get out the image much cleaned up. So suppose that purpose of this one is that say the application was face recognition, and we got a picture. They capture whether this lady is a criminal or the good person that we are looking for. We don't know, but we want to identify her. But with this picture, it's very difficult. But with this filtering, simple median filtering, we already have a very good idea about her face. Then, of course, with some more of the filter applied, then it can be cleaned up and much clearer pictures we can get. Then bilateral is a nonlinear and iterative filter. So you do those neighborhood and weighted average. So it's a kind of Gaussian average, but it's a keep doing not just once, but do many times. That's why the Gaussian and then those cleaning up operation done many stages and results in much better results. So this is the original picture and the bilateral here. So here we see clearly that this one looks clearer, but better one is this is another example I pulled out. So original one, this is fingerprint the image. Say suppose this was taken about 30 years ago. So it's not very good, not very clear. So anyway, we got those fingerprints in here, and a lot of those salt and pepper noises. So what we do? Then by using bilateral filter in multiple steps of those iteration, that we see those things are much better. So you can identify, can you, do you think that the machine can recognize the fingerprint pretty easily here? I don't think so, but this one you can do with the making higher resolution. So some speckle noises can be reduced. So doing some more times, then you can get the whole thing cleaned up. So this early vision part does using this filter we covered that by applying like a median filter and then averaging filter and sharpening filter and Gaussian filter, that you can generate the pretty good the results. Then there's the image pyramids that again that this one is more like a grid issue. So what it is that as I told you that there's a different layer. So go to Google Map or Google the Earth or some the other mapping utilities. Then it gives some kind of the highest level or the very top level whole Earth in one chunk, and you go deeper, then it gives more detail. So that can be done by, of course, the map exists at the lowest level. Then those things will add up or the combine together. So the I'll just pass this one. So in the pyramid part, that usually each level goes 4 by 4 averaged. 4 by 4 average. So each time it is reducing half on one direction, but in left and right, the horizontal and the vertical. So it's area, so it's a 1/4 of the size. So as time goes on, if you go to 10 level, then it's the 4 power of 10. That become several million. So it is pretty much the smaller scale, smaller views. So in other words, that it seems to be that each time it is you reducing just half of them. Then you will preserve enough detail at each level, and at the same time you can get the top part. But the calculation goes so fast that original map part given, and then you get cut it up. Actually, in the middle part can be saved somewhere. So this is being saved, and each time that you are reducing half. Suppose this is the 400, then this will be 200 by 200. Then here 8 by 8, 4 by 8. Then here 100, 100, and then 25, 25. I'm sorry, the 50, 50, and 25, 25. Anyway, it's a keep reducing it. So level-wise, it goes up all the way. So you got the image or data in certain the middle level, and from there you can create one. That is, if you want to have from bottom one to top one, is a whole earth itself, and this is all the detail of the street. It takes at least the 15 levels. So calculating 15 levels of the reducing, computer can do it, but that again takes connection time, like data must be brought it in. So it can be done by storing or keeping several different level of those image data, and from there, if it is more, then you can make us shrink it out. But anyway, it's a very smaller part. So original one is the total. The image part, it's just a so-called sampling. So you have a 512 by 512. You put that one by 256, 2 by 6, like that one. So as it goes on, it's a blurry, less clear. But if 8 by 8 by, then there isn't much you can get the detail. So it gets all the pyramids created. So this is also important thing. So suppose for example, that when you are using like the certain the web hard or some I don't know whether actually YouTube does that, but all the days it used to do that. If you upload a certain file in certain intensity, they reduce it for you to save the space. So that can be done more dynamically. So this view pyramids is very helpful in that. Then aliasing is that by going on when video goes in, the aliasing is that out of sync. That's what it is. So when it is about the video part. I think I will talk about the video related the image processing later part. But the video is a sampling. So in other words, that the typical movie, good old days, was the 16 frames per second. So each second it has 16 frames. So our eyes see what is a film when we are looking at them, they are fixed. That's like a photography. But if that is shown and erased, that is removed, and shown again with a slightly different kind of changes, then your eyes will have a previous image and superimpose your new image on top of that. Typical videotape, the old tape like that one, then they have 1 frame here, 1 frame here, 1 frame here, one frame here. So there's a rollers, the reading, displaying, reading, displaying. But you do this one, like I say, the 16 per second. Then this will give you pretty much of the smooth movement. But one problem is that whenever you look at those the old Western movie, then they have this cart. This big wagon is coming. Wagon like that one. When it is on, then this one seems to be in the beginning, it's just starting. So when they are moving, then this one, the wheel is moving. Then after for a while, then it goes faster. Then it doesn't go. It's kind of one place of it goes slower and stops and go backwards. I'm sure you have seen that one. That kind of a misalignment is called aliasing. That is that you are putting X number of frames. You have just kind of a cutting a little bit, and in a way cheating your the eye, say that as if it is smooth. So it is different from what you are looking outside, and actually the wagon is moving. In the movie, then you got 16 frames per second. Sometimes it is 8 frame, and they are showing same frame twice. So in a movie projector, that it shows one. It is not like suppose that you have a film and it's just pull on the projector, nothing is moving. What it is moving, junking up. So it shows, and there's a moving up. Meanwhile, there's a shutter coming in, so the light is blocked. So for a while it is dark, very short time. Then open up, next frame comes up and open up. So it shows those frame, chunk, but faster, 16 times a second, or sometimes same frame twice in within those the time span. So 8 different frames showing twice. Then your eye, your back of your eye, that your retina have the old image still stored here. Like when you look at the bright objects and close your eyes, the very small duration you see some kind of image in your, as if you see it. So that's called the remaining image. So that images are shown in here. So in video operation, then there's the aliasing that's looking like going backwards. So sometimes you may want to handle these issues by different kind of the calculations. So instead of so in other words, that the wheels keep moving. So it takes one in the suppose those different that's called the spoke. So from this one goes to here, and this one goes to here. Suppose it took 1/16 second, then it will be looking exactly the same location. So when it's very slow, it is moving in like 1 round per second, or the half a second. Then it looks like those things are turning correctly. But it goes faster, and it takes just 1/16 of a second to move. This one moves over here because it goes a little faster. Then you don't see this one because all those say 8 or the 10 those lines, spoke it is called, is the same shape. So you see as if they are staying same place. Then if we go faster, then it looks like it's a little bit lagging behind. So they looks like turning backwards. So that kind of the misrepresentation, that one is that sometimes misleading or doesn't look realistic. So sometimes they are changing that by adjusting it. So similar idea that something not in the right places that can be removed. That is called resampling. So in here we got a blank those circles. It's more like the salt and pepper. This one is the salt noise, and this pepper noises. then it can be reduced by resampling those areas. Okay, so keep going on with the Gaussian. So in relation to Gaussian pyramid, this one's supposed to, I skipped that one, so I'll just pass this one. And the Laplacian pyramid, again, that this is to make it as realistic as possible. When PowerPoint, when running it on the PowerPoint, that it is not showing, but in here it is showing. So I'll pass that, and the sharpening again can be done. Okay, I'll quickly go over a Fourier transformation. Fourier is Jean-Baptiste Fourier, who's a French mathematician who were born in 1760 something, and he worked most of his life with the Napoleon and as academician, and sometimes he was a governor, and a very smart guy. So he just somehow thought about that. Okay, can we change our data from those wave into space values, so wave and spectrum, that kind of a signal. So first he did it by heat transfer, that one metal, when it is heating something on a metal, then the heat will be moving it over like that one. So heat transfer was his main idea. So what it does is that it is used for reducing the noises in the sound. So sound is a wave, and then can we change that wave into some kind of a spectrum or some kind of a sine cosine values? And then so the spatial domain, that is a space-wise, that the domain into the frequency domain, sine or cosine, that kind of idea. So what does that mean? Again, if we want to know all the more detail, then this one has a pretty good sequence of videos, so that talking from background to the detail. So if we are caring about it, idea is that, remember this picture we saw before. So each line is that when we look at those intensity, that goes with this kind of a line, or this kind of a waves. So this space can be some kind of a this up and down sequences, because it's continuous, left to the right. So it's a sequence going up and down, up and down, up and down. So can we make some kind of function to it? So there is some noises. If we have some sine cosine value for this kind of curves in general, then by applying it, then this detail will be removed. That's the idea. So in fact, there is the typical spatial domain of x value. Time, actually, x is time. Time changes, then you got different value. There's Euler there. Actually, I'm not going to talk about that. No time. But this 2 pi theta, that one, actually, what happened is that e2 pi theta plus 1 equals 0 is Euler's equation, or uniformity. So this whole thing is -1, this one. So you can apply that one. So and then his equation says that E form is a cosine and sine. So in other words, that any kind of spatial values can be converted into sequence of sine and cosine functions. So if you just apply the sine and cosine function, trigonometric function, you will end up getting much smoother and simplified equation. So this one is fx, then this x is a curve form. So spatial effect of going up, down of those value by time, that can be by this the waves, like that one. So again, this one is pretty advanced in terms of the mathematics. So I'll just pass it. There are many wave frequencies, and then those trigonometric functions to apply to, but the best way is just showing what it is happening. So what it is that you have this kind of a curve. So what it is this one is a little lower part and suddenly higher part and the lower part of this kind of thing. Then by Fourier transformation, first of all, they're removing that the up and down by they're removing those average by those the averaging filters or the Gaussian filter. That all those fluctuation can be dialed down. Then convert that one into simpler sine cosine value. So the result looks like this way. That this is original picture, but you see there's a band there, that band effect occurring. That is that this kind of thing is occurring regular basis. So what you can do, there's a white line is occurring regular basis like this. So by putting that on, and then by making over all sine cosine values, that you can get rid of those stripes. That's what the Fourier transformation can do. So the reducing and the cleaning our image can be done by Fourier transformation. This is a little hard part, and I don't have enough time to talk detail, but just remember the name Fourier. F-O-U-R-I-E-A, Fourier transformation. Anyway, so there are a few of those the calculator applications of Fourier transformation, and then some detail about how to use that. So this kind of way the line can be changed into Fourier transformation. And then others, OpenCV, this one I already showed before. And then soon we'll talk about those deep learning. So the Keras is one of those TensorFlow, and the Keras being part of those deep learning utilities by Google. And Cholet wrote a book about that, and he had a lot of good software. So deep learning with a Python notebook. Actually, I have that book, and I put this one in PDF format into the our library. I mean, the archive, so it's in there, so you can get those books if you want. Okay, I think that's all for the day.